Hi everyone, I'm Anthony, and this is joint work with my colleagues Ransalu and Fabio. In this talk, I'll discuss how to quantify uncertainty of occupancy in large-scale unstructured environments by adapting pre-learned parameters to new domains. Consider the problem of estimating which areas are occupied and which are navigable using a LIDAR point cloud. Let's focus on a small part of the environment. What we are interested in is estimating the occupancy probability of an arbitrary point x star in the environment given the point cloud B. We are not only interested in a deterministic estimate, but also the predictive uncertainty. Quantifying uncertainty is crucial for safely operating robots in unknown and dynamic environments. Since we are interested in modeling epistemic uncertainty rather than using occupancy grid maps, we use Bayesian Hilbert maps. Bayesian Hilbert maps models the environment as a continuous function f with parameters theta that must be learned. Because we model uncertainty, these parameters are probability distributions rather than point estimates. We only show the mean occupancy map on the right. Red indicates occupied areas, blue indicates free areas, and green are where we are not sure. Bayesian Hilbert maps rely on a particular kind of embedding called kernels, which are a particular way of continuously representing our LIDAR data. We can have stationary kernels, as seen above, which assume a consistent spatial smoothness, or non-stationary kernels like on the right, enabling us to capture sharper boundaries and smooth regions of the space equally well. Non-stationary mapping, while extremely expressive, has some limitations for large-scale implementation. The problem with all the previous methods is that for large environments, parameter estimation is computationally expensive. This makes traditional probabilistic mapping techniques inadequate for online learning. This invites the question, how do we estimate parameters without relearning from scratch for each new environment? Our solution to the above problem involves the following contributions: a theoretical framework for online parameter transfer, online and efficient large-scale probabilistic mapping, and intra and inter-domain parameter transfer in real time. Our proposed method is based upon the theoretical foundation of a field called optimal transport. Optimal transport, at a high level, is concerned with the question, how can we move mass, in our case, an empirical probability distribution, from one location to another in the most efficient way possible? In this example, we have two empirical distributions, a red square on the left as the source and a brown circle on the right as the target, both representing LIDAR hits. Our goal is to find an optimal association between the two distributions. To do this, we must, firstly, determine a cost matrix D that represents the distances each source sample must travel to the target according to some metric, and secondly, the coupling matrix E star. This coupling matrix ultimately tells us how to transport from the source to the target in the most efficient way. This animation demonstrates the interplay between the solution of the coupling matrix and the geometric coupling with the parameters shown in blue and purple. We can see that the parameter transfer is robust to various deformations of the target. What our method, named Parameter Optimal Transport, or POT, means in practice is that we are able to take candidate models that have been previously learned and simply transport the closest correspondence. We demonstrate our parameter transport framework on multiple tasks involving both simulated and real-world data. In this simulation experiment, we demonstrate transfer from one part of the domain to the rest. Next, we wanted to demonstrate parameter transfer across different domains. This experiment covers various transfer learning paradigms such as simulation to real and adapting from static to dynamic environments. Next, we wanted to see how our framework could apply to the real-world KITTI dataset. Finally, we demonstrate how POT can be used as an informative prior in Bayesian inference to further refine map quality. We term this refinement operation repot. In summary, we've presented a theoretical framework for online parameter transfer for efficient large-scale probabilistic mapping. Thank you.